Okay, so hello everyone. Welcome to our communication laboratory project. It is called audio steganography, or hiding confidential image data in an audio file. Now let's first get familiar with what the term steganography actually means. It is basically hiding a secret message in an ordinary message and later getting it extracted at its destination, so that the existence of the secret message is discrete. That means it is camouflaged into a data, so that its existence cannot be perceived. So based on in what type of data the secret image is hidden, it can be classified in three types: image, audio, and text. So we're trying to hide the secret image in an audio file. Now let's see how it can be done. If we pay an insight into the methodology, we can actually break it down into three stages: encoding, decoding, and reconstruction. Now let's look into how the encoding is done. Firstly, there are the most used algorithms are phase coding and LSB. Now we have chosen to use the LSB algorithm because it is much more simpler to implement and also quite effective. Now let's see how the LSB algorithm works. First, you get the secret image that you're trying to hide. It has to be converted to grayscale, which is a black and white version of the image. So you will get an array of the pixel values, and they have to convert it to their binary representation. The next stage is to quantize the cover audio file where you will hide the image into 8 bits. So let's see how the quantization works. Now the audio file can actually be represented as variations of the amplitude with time. Now if these amplitude values are sampled and then quantized into discrete levels, the audio file can then be represented as a sequence of these quantization levels instead of the amplitude values themselves. Now this array of quantization level values can be it has to be converted to their binary representations. Now in the next step we are replacing the last bit of each value of those elements of this array with a bit of the pixel values, with a bit of the pixel binary value. So each bit will go into the last bit of each byte of the audio file. Now after the levels have been modified, the carrier audio file is constructed. Now let's see how now an example can actually demonstrate how this actually happens. Will make things easier to understand. Now let's say, for example, a pixel value is 161. Now this in binary is 101000001. Now these bits will go into each of these levels. So let's say these are the amplitude levels of the audio file. So the first value is 144, which in binary is this. So the last bit is 0. So this bit will go here into this last bit. So this has to be replaced with a 1, and this becomes 145 as a result. So the level has increased by 1. This means the amplitude has increased by a level of 1. Now the next bit is 0. So as you can see, the last bit of 140 is already 0, so it doesn't need to be changed, so it remains unchanged. The next bit is 1, and so this bit has to be changed, replaced with 1, and so it becomes 155. So we can see that the levels are changed just by 1, or it stays the same. So this means that the amount of noise added is not too much. Now after the quantization levels have been altered, they have to be converted to the amplitude levels. This is the reverse of the quantization process. The amplitude levels corresponding to the quantized levels are obtained, and then this can be used to write an audio file which is basically the carrier audio file which contains the secret image. Now let's listen to the audio file before the image is hidden. And after the image is hidden, it sounds like this. So you can clearly see that there is not much difference between the two audio files, so the image has been hidden discreetly. Now let's see how the decoding is done. Now you get the carrier audio file that has been sent to you by the encoder. Now the first stage is to quantize it like it was done before, to obtain the quantization levels in binary of this carrier audio file. Now if we isolate 8 of these alternative bytes of the binary levels of the quantization levels, and then convert them, each of them, into binary, and we can extract the last bit of each of these values. So this forms a sequence of 8 bits, which actually represents a 1 pixel value. So if this is converted to decimal, we get 161. This is the recovered grayscale value of 1 of the pixels of the secret image that is sent. So in this way we can get the rest of the grayscale values as well by isolating the next 8 bytes of the quantization levels and extracting their respective last bits. In order to reconstruct the image, we obviously need to know the dimensions of the image that has been sent. So these two data has also needs to be encoded into the audio. So for this, we have actually hidden the length data in the first 10 bytes of the audio, and in the next 10 bytes we have hidden the height value. So this is converted into a 10-bit binary number, the length and height. So if the dimensions are greater than 1024, the encoding process cannot be done. So what happens if we insert a higher resolution image? It will actually be cropped by the encoder so that it's not greater than 1024. So you get a one-dimensional array after the decoding process. This array stores the pixel values, the grayscale pixel values of the secret image. This has to be converted into the two-dimensional array so that it looks something like this. These are the grayscale values of the image. Now this two-dimensional array can then be used to write an image file, which is actually the reconstructed image finally. Now here we can see a sample input image and the reconstructed image. Now you can observe that it's a black and white version of the input image. Now why didn't we get a colored version of the image? Because we have only transferred the grayscale values, not the RGB values, and it is not possible to recover the RGB values from the grayscale value. So if we want to transfer a colored version of the image, then we have to transfer 3 times as much data. This means for each pixel we have to transfer 3 times as much data, which requires more encoding time. So we have chosen to get the black and white version of the image. We have developed a graphical user interface for the Steganography tool, which we will now explore. We have packaged the user interface into an app which can be accessed from the Apps tab here. If you click on this app, it will launch and this window will appear. Now we can see that there are 2 buttons here, encoding and encode and decode. First let's encode a secret image into an audio file. So for that we have to first press on the encode button, and this window will appear which will prompt you to select the image that you want to hide. So let's say we want to hide this picture of a kid. Open, and see that the encoding process started. It is indicated by this green light here. Now you've been prompted to select an audio file in which you'll hide the secret image. So let's see, I select audio file. Now encoding process is now started, and you can track the progress here. This shows the status and the percentage completed. Now you can see that the encoding is in progress. You can track the progress in this gauge here. And now we can see that the encoding process is complete, and we've been asked to enter the name of the encoded audio. So let's say it is Stego audio. You can save it. Now if you press on this button, it will show in which folder the audio has been saved, and you can press on the play button to play the encoded audio. Listen to it. Now the audio file that has been produced here can be sent to the receiver via email.
Today I got this mail from a friend attached with an audio file. The audio file contains the secret image. So I will use the same MATLAB app to decode it. I press the decode button and it will ask for a password. The password is Pokemon. Now I have to choose the audio file. The decoding has completed and it has asked for a name for that image. Now I press the view image button. The secret image pops up. I hope you guys enjoyed the video. Thank you for watching.